right, so section 4.4 is more properties that help us take the Laplace transforms of more complicated functions so we can solve even more types of differential equations. So just like with before the last section, what I'm going to do is I'm going to start off with a list of things that you should copy down to that reference table that you have for Laplace transforms. And it's going to be everything we'll go over in this class. And then what's going to happen is you'll have them in one place to use. And we'll just go through our examples one by one that kind of show you how to use them. So the first one is going to be the Laplace transform of t to some power n times f of t is going to be equal to minus 1 to the nth power times the nth derivative of capital F with respect to s, where we always have that L of little f is equal to big F. And this is only going to hold for n being whole counting numbers, 1, 2, 3, so on and so forth, so that derivative makes sense. The corresponding inverse property is going to be that the inverse Laplace transform of negative 1 to the nth derivative of f with respect to s, is t to the n times f of, be really clear there, little f of t. Again, you don't have to copy both the forward and the backward direction if you don't want to. And then the second property we'll talk about is that L of f star g is equal to capital F times capital G, where L of g is capital G. And that star notation is something called convolution. We'll talk about them more later. But for now, just copy down in your reference that f star g is an operation where you go from 0 to t of f of tau times g of t minus tau, integrating with respect to tau. And I hope it's really clear that these letters right here are different from t. And then the inverse of that property is that the inverse Laplace transform of a product of two functions is that special convolution star operation. And so I'm going to put that in a box. Hopefully you put that somewhere that's going to be handy to refer back to. I'm going to go ahead and do the first example because I think we can fit it in here. We're going to be trying to use that property that L of t to the n times f of t is equal to minus 1 to the nth derivative of f with respect to s. And the example we're going to apply that to is L of t sine kt. So we're going to just sort of pull the different pieces out of this. We have t times sine kt, so we've got t to the n for n equals 1. And then here, my little f is equal to sine kt. So that means my capital F would be equal to k over s squared plus k squared. And since I have this n equals 1, I imagine I'm going to have to take a first derivative. So I'm going to go ahead and do that right now too. df ds would just be equal to 1 over s squared plus k squared squared. And then I would multiply by a minus 1 and a 2s to round out that derivative. So all I did was I took the derivative of this quantity with respect to s. And that's minus 2ks over the original denominator squared. So now, if I wanted to go ahead and take my L of t sine kt, I think that's going to be minus 1 to the nth derivative of f with respect to s. That's minus 1 to the 1, df ds. That's minus 1 times minus 2ks over s squared plus k squared squared. That's just 2ks over s squared plus k squared squared would be the answer right there. And I'm just going to note that you're going to want to keep this derivative in mind, that the derivative of k over s squared plus k squared, the thing that you get when you take the Laplace transform of sines, is that minus 2s times k over s squared plus k squared squared. So just remember that. It's going to come up a lot in this section.